Hey everyone. So in this lecture, I'm going to talk about taking the binomial regression structure we talked about in the last lecture and how to apply Bayesian methodology to that, what the likelihood is going to look like, how to come up with some reasonable priors to deal with that model. I hope you enjoy it, and next time we'll be back with some discussion of data sets that this actually applies to. Let's pick up with our discussion of how to implement a binomial regression, specifically a logistic regression, in a Bayesian framework. So again, I'm going to go back and redefine my pieces that I'm going to need for this. So let yi be some binomial response data with yi distributed binomial ki pi. Let xi be a corresponding covariate vector and beta a set of GLM parameters such that pi is equal to, like I said, we're going to do the logistic model that we've talked about, e to the xi beta over 1 plus e to the xi beta. And this is our standard logistic regression model for doing binomial data here. So this is our setup. Yi is going to be binomial ki pi, and xi is going to be a covariate vector that gives us this pi is equal to e to the xi beta over 1 plus e to the xi beta, which is the logistic function. Okay, so if I'm going to be a Bayesian, then I'm going to need to identify a few key pieces for me to use here. So I'm going to need parameters in this model. I'm going to need priors for those parameters and a likelihood to relate the data to those parameters. So first of all, what are our parameters? Well, normally in a binomial model, our parameters would be the p's, the probabilities of successes, and we would assume that we have the number of trials in each of these yi's known. So p would be our parameter, but here p has a perfect relationship to some function of xi beta. And so what we're actually going to refer to as our parameters here, instead of having a separate p for each y, which is a bit more like an ANOVA type model, a non-parametric type model, we want to just look at the betas. The betas should be a smaller parameter space, such that just knowing the x's is going to give us everything we need to know about those probabilities. Just knowing the x's and the betas is going to give us everything we need to know about those probabilities. So now in a normal regression model, we often have to worry about both the betas and some error variance. Why do I not have an error variance I need to worry about in a binomial regression model? Well, this is one of the things that makes binomial regression a little easier for us as Bayesians than normal regression. The binomial distribution, where I have known number of trials, this guy is a one parameter family if I have no number of trials, because my only free parameter here is pi. And so if I know pi, I know the mean of this distribution, I know the variance of this distribution, I know everything I need to know. So if all I need to know is pi, and I get to see yi and I get to see xi, then that's equivalent to saying all I need to know are the betas. I don't need any dedicated variance terms here to worry about. And so the only parameters I care about in a binomial regression model are going to be the betas. Okay, so what are our parameters? Our parameters are the betas. Now I'm going to do the likelihood second, because we're going to spend quite a bit more time on the prior. So what is the likelihood going to look like for this model? Oh, the curse of inconsistent capitalization. Okay, so likelihood for a binomial regression model. Well, I know that my data, my response data y, are going to be binomial ki pi. And I know that pi is going to follow this function. So in the previous lecture, I talked about this function here being what we call g inverse of xi beta. But I think I'll just write this out the long way. So likelihood for a binomial regression model, L of, well, it's going to be beta here, because beta is the set of parameters that I'm going to be updating. L of beta given y and x, all of my y's and x's. So what's the joint distribution here? Well, these are going to be independent binomials, right? So the joint distribution is just going to be the product of all of those independent binomials. I'll go from I equals 1 to n. And then, let me lose the equality, because remember, if we're being Bayesians, we usually only care about this up to proportionality. And so let me just do proportionality, and then I don't have to worry about the n choose k, or the k choose y terms on these guys. I can just deal with the likelihood portion that contributes to beta, so I don't have to worry about that guy. So this is going to look like, up to proportionality, pi to the yi times 1 minus pi to the ki minus yi, which is going to be the same as saying if I substitute in for my pi's, e to the xi beta over 1 plus e to the xi beta, that all to the yi power, because that term in those parentheses there, that guy is pi for us. And then what is 1 minus pi? Well, you might remember I played around with this a little bit on the proof of the logistic and logic functions being inverses of each other last time. That 1 minus pi actually has a really nice form. This is just 1 over 1 plus e to the xi beta. And this I will raise to the ki minus yi power. And this is my likelihood for, I should say, not just a binomial regression model, but a logistic regression model. So this is what my likelihood is going to look like. This isn't too hard to deal with. I have now a function here of beta that depends on yi and xi and ki. I need to know my ki's here too. But this is a pretty easy likelihood function for me to play around with. So, third question. What are the priors I'm going to use? So I could consider a few different types of priors for the betas, but let's think about what's going to happen in this model for certain priors. So let's start with just, you know that I don't like improper reference priors very much. Let's think about what happens if I use improper reference priors. Doing this on the betas. Let's do betas subscripted with j, since we're subscripting the data points with I right now. So I have my X matrix here. Each X is a covariate vector, and beta is a set of GLM parameters associated with that covariate vector. So in the simplest regression model, we usually have like an intercept term and one covariate variable. So beta would, in that case, be two-dimensional. I would have my intercept beta term where my X matrix would just contain a column of ones to correspond to that intercept, and then I'd have actual X data for some covariate in the second column and a beta corresponding to that. So let's let j down here be an index over the number of covariates that we're dealing with, the number of columns in our X matrix. So if I use an improper reference prior, for example, this is one way I could write an improper reference prior here. The idea here is for bj normal 0 infinity, this is your concept of a flat prior over the real line, basically. So I'll just do an equivalence here. I mean, they're both improper, so you could really write it either way. Neither of these is a proper probability distribution. You can't actually do this. But so the idea of a flat prior over the real line. What happens if I do a flat prior over the real line? Well, we talked before about how x and beta are going to behave in this logistic setup. And so remember, I've got e to the x beta over 1 plus e to the x beta. If x beta is 0, this is going to turn into 1 over 1 plus 1, so 1/2. If x beta is about 1, then I've got e to the 1, so I've got e over 1 plus e. E is close enough to 3 that we can say that that's about 3/4. And if I've got x beta negative 1, then I'm going to have this whole term up here is going to turn into 1 over e over 1 plus 1 over e. So if E is about 3 again, what am I going to have? If I get a common denominator for these things in the denominator of this fraction, then I've got E plus 1 over E. And I've got up here E over E. I can cancel those guys. What I'm going to wind up with is I'm going to wind up with my 1 over 1 plus E, effectively, or about 1 over 1 plus 3, so about 1/4. So if I've got x beta equals 0, this guy is going to be 1/2. If I've got x beta equals 1, it's going to be about 3/4. If I've got x beta equals -1, it's going to be about 1/4. If I have a flat prior over the real line, now we don't know what our x data is going to look like, but for a flat prior, it doesn't matter too much. Usually we like to standardize our x data so that x has mean 0 and it lives on something like a standard normal space. I'll talk more about that in the next lecture after this, why standardizing our covariate information is useful for binomial models. But if we assume that we've got x data that is in reasonable values, then we know that this guy moves pretty quickly because we've got an e to the x beta term. So one way I like to think about this is, okay, I've talked about x beta equals 0, x beta equals 1, x beta equals -1. What if x beta equals 3? So again, I'm going to do my substitution of e for 3 when I think about this. So 3 to the third, that's 3, 9, 27. 27 over 1 plus 27, so 27 over 28. We're looking at, that's close enough to 96% right there. And if we do it the other way around with a -3, we're going to have close enough to 4%. So if I've got an x beta of 3 or -3, I'm already getting very close to having a probability of 1 or 0. I'm not at 1 or 0, obviously, but already with x beta, with just the x beta sum adding up to 3 or -3, this whole probability has skewed pretty heavily towards being sure that I'm either going to get a success or a failure. If I go to 4, it's going to be even more extreme. I've got 81 over 82 versus 1 over 82 or thereabouts. So really, I don't want x beta to get much above 3 or below -3, or maybe if you want to be a little more generous, above 4 or below -4. Values that get outside of that range tend to give me very extreme probabilities, and so I tend to not want those too much. If I put an improper reference prior, like a flat prior over the real line on the betas, what that's going to do is it's going to mean that these don't mix very well when I start doing Bayesian computations. And it's going to be pretty easy for these guys to get out of hand on me and go off to weird numbers. Now, in practice, if I've got a lot of data, I'm probably not going to have to deal with that problem too much because data is going to overwhelm my priors. But if I'm dealing with a smaller data problem, or I'm dealing with a covariate space where I don't explore the covariate space particularly well with the observations that I've got, then having a bad prior here can cause me some trouble down the line. So again, I'm not a big fan of using improper reference priors. Proper reference priors I'm cool with, but improper reference priors can cause some complications for me. This is not a great place for me to be using improper reference priors. It always pays to think about the priors you're going to use. So I use improper reference priors. So I use improper reference priors. I'm going to start getting values of beta that make pi get very large or very small, which are not things that I particularly like when I'm doing a binomial regression. So the point I always come back to on priors is it always pays to think about how our priors are going to translate into the predictive space. Here I'm going to be getting p's out of my priors. I'm going to induce a prior on pi for any prior on beta. So I'm going to have probabilities. What's going to happen on my prediction space? So if I'm talking prediction space, I'm talking some future set of y, some future set of response observations given covariate observations x. Now, if my PIs are very close to 0 or 1, my predictions are going to be not particularly interesting in that case, because I'm either going to always predict successes or always predict failures if my PIs have gone extreme. That's not how data tend to look if we're doing logistic regression. If I know that I'm getting successes or I know that I'm getting failures given a particular covariate setup, then I probably don't need to be doing the work of running a logistic regression. So it's fairer to assume that for any set of covariates, I'm probably going to want to see some successes and some failures. And the proportion of successes and failures is going to depend on the covariate vector I get. So if I'm getting predictions that are all zeros or all ones, that's not a great thing to do. Okay, so I want to think about priors in the predictive space. How can I make priors using that? So let's go back to the structure of the logistic regression for a minute, and we can talk about how to understand the beta priors. Well, if we have G inverse of xi beta is equal to e to the xi beta over 1 plus e to the xi beta, our logistic model, which we're calling pi, then let's go back to what is g of pi. G of pi is going to be, if this is the logistic function here, this is going to be the logit function, which is natural log of pi over 1 minus pi. Now we can use that to our advantage here with the connection between these guys. So let's consider an observation. No, let's take a step back. Let's think about this in a very simple binomial regression model. So I want to talk about what the x vector is in particular to get into this. So a very simple binomial regression model where xi has two elements. Xi is equal to, and I'll write this as a column matrix, 1 and xij. I don't need a j, I just need an xi1. And this gives me an intercept and a measured covariate. So my X matrix, if I consider the X matrix for the whole problem, is going to look like because now I'm going to turn these into row vectors. 1, x1, 1, 1, x2, 1, dot, 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 1, x, n, 1. Which means that beta is going to be beta 1, beta 2. Or actually, let's do beta 0, beta 1, so that my 1 here can match my 1 on the x's. Okay, so this is a setup we want to consider for understanding how to build priors on a regression model. We've got just two elements to x. We've got an intercept and we've got a measured covariate. Now, imagine that we're looking at an individual with x I1 equal 0. So I'm going to zero out that measured covariate. Then g of pi is equal to, well, it's ln of e to the xi beta over, let's write this a little differently. Okay. Let's do the following. Okay. E to the xi beta divided by 1 plus e to the xi beta. And then remember, this is going to be 1 minus p down here, so I'm going to have 1 divided by, same thing, 1 plus e to the xi beta. And so our denominators for those two fractions will cancel. This whole thing is going to turn into ln of e to the xi beta, which means this is going to be xi beta. Get myself a little bit more room. And in this case, with xi1 equals 0, this is just going to be beta 0. So if I have an individual with xi1 equals 0, then that individual's g of pi, the log odds for that individual, are just going to be equal to the parameter value for the intercept term. So now let's look at an individual with xi1 equals 1. G of pi is again going to be xi beta is going to be now beta 0 plus beta 1. Okay, so that means that before I do the next bit, let's stop and talk about where we are. Okay, so I've got a beta 0 here. I've got a beta 0 plus beta 1 here. Now, if I want to isolate beta 1, so what's my goal? I want to make priors for beta 0 and beta 1, right? Well, I've found something that's beta 0. So in a minute, I'll be able to talk about how I can use this whole setup to give me a prior on beta 0. I also need a prior for beta 1. And based on this, if I have let's call this xi prime 1, pi prime, xi prime beta, to distinguish this from the one above, because I want to be able to talk about both of these at the same time. Because what I've got is beta 1 is going to be equal to g of pi prime minus g of pi. So relating these two. Okay, so now I've got some way of talking about beta 0 and beta 1 separately. What does that get me? So, like I said, when I want to think about priors, I like to think in prediction space. Now, what I'm going to talk about here is going to work very well for eliciting subject matter expert priors, but it's also going to work well for just thinking about, do I have a reasonable prior for these data? So, we now have two hypothetical covariate vectors. And I'll call those xi and xi prime, like I had. We can think about the probability of successes on binomial trials we can think about the probability of successes on binomial trials for our response variable y given these covariate vectors. So let's put that in some sort of context. Now I'm going to spend the next lecture talking about one or two extended examples using binomial regression, but just as a toy example for the moment, because let's be topical, let's talk about diagnostic testing for COVID-19. So I'm doing a diagnostic test for COVID-19. That is my y response variable. Diagnostic test is going to come back with a 0 or a 1, and whether I get a 0 or a 1, whether I get a positive test or a negative test, is going to depend to some extent on some set of covariates. So those covariates could be something involving an individual's personal risk and population risk. So I can think about my intercept in this as modeling to some extent population risk. What percentage of people in the population are currently infected with the coronavirus, that's going to help me figure out where to put my my beta 0. My beta 1 is going to be dealing with personal risk for this individual that I'm testing. And so my beta 1 is going to incorporate some information about this individual. Okay. So, like I was saying, beta 0 is going to represent something about the population as a whole. Beta 1 is going to represent something about an individual. Question 1. What is the probability? Oh, let's write that I better. Let's write that B better. What's the probability of testing positive for an average individual in the population? Not doing a great job writing there. Sorry, guys. So probability of testing positive for an average individual in the population. Now, I talked before about I usually center my x's. I usually center my covariates. Centering my covariates is what lets me talk about an average individual for the population here. So for somebody with covariate 0, for covariate level 0, measured covariate level 0, somebody who is in the middle of whatever distribution I'm talking about for whatever covariate it is that I think matters. So for somebody who is average, what's the probability of testing positive? Well, for COVID-19, we probably think that about 2% of the US population has currently contracted COVID-19, has contracted the coronavirus. That's off the top of my head. That's based on some epidemiological projections for, given the current infected rate that we have, what the actual infected, or given the current diagnosed rate that we have, what's the actual infected rate we might have. So let's just say this is about 0.02. Well, if it's about 0.02, that's my best guess for that probability, right? And let's say that's no higher than 0.10. Okay. Probability of testing positive for an average individual is 0.02, and it's no higher than 0.10. Well, we know that I can do this sort of back conversion. G of pi is beta 0. G of 0.02 then should be something like my expected value for beta 0. Does it make sense how I'm getting that? So I'm saying that 0.02 is my best guess for the probability of the probability of a positive testing result for somebody who has covariate level 0 on my measured covariate, somebody who is average. So my best guess, I'm going to move that through here, G of 0.02 is going to turn into B0, but that's my best guess. So I want to talk about that as my expected value. What is g of 0.10 going to be? Well, I need a distribution on beta 0, right? And so this is going to be writing this a little differently than I might normally write this. The expected value of beta 0 plus, let's do 2 times the square root of the variance of beta 0. So I'm just saying that a probability of 0.10, this is now going to be 2 standard deviations above the mean for beta 0. So I'm saying this is the highest I expect this guy can get. So highest I expect this guy can get, I want to move up to the 97.5 percentile on this, or approximately the 97.5 percentile. Now, obviously, I might want to do less than that. I might want to do something like the 95th percentile or the 90th percentile and drop this 2 to a 1.65 or a 1.2 or something. So depending on the level of confidence I have in this probability 0.1, I'm going to change my multiplier to the standard deviation down here. But what I've got here is I've taken those statements about probabilities and I've back translated that into statements about the expected value and the variance of my beta distribution, or of my distribution for beta 0. So now, instead of having this reference form, where did I have it? Oh, it's way up here. Instead of having this reference form normal 0 infinity, now I can start talking about beta 0 having a prior centered somewhere meaningful and with some meaningful variance. So that's my first question I want to ask. What's the probability of testing positive for an average individual in the population? Second question I want to ask is, what's the probability of testing positive for somebody who's a standard deviation higher on my measured covariate? So let's say my measured covariate is, let's say I have information on cell phone movement. So often Google will keep track of where your cell phone is. This is how it can tell where work and where home are for you just when you ask it, because it's seen that you're in these two locations pretty frequently. So Google has sort of just in the background usually some information about how their cell phones move, what cell towers are providing receptions for reception to what cell phones. And so you can get a pretty easy measure of how much somebody is moving. So let's say, what is the probability of testing positive for someone who is 1 standard deviation higher than an average person for how much they're moving around? So this person is clearly out more. Maybe this person has an essential job that they need to be going to. They can't quarantine like some other people might be. And so we think that the probability that this person is going to test positive is a little higher than in the general population. So let's say that this is about 0.04, no higher than 0.15. Now, this is going to be a little harder because I know that g of 0.04 is going to relate to not just beta 0, but beta 1. Okay, so how can I mess around with this? Well, like I said, instead of considering that raw, we know that beta 1 is equal to g of pi prime minus g of pi. Well, what is this? That's the same as saying ln of pi prime over 1 minus pi prime minus ln of pi over 1 minus pi. Some of you may already see the trick here, is equal to ln of pi divided by 1 minus, or sorry, pi prime divided by 1 minus pi prime divided by pi divided by 1 minus pi. This is the log odds ratio. So I've got an odds here, I've got an odds here. I'm taking odds divided by odds, so I've got an odds ratio, and I'm taking the log of the odds ratio. The log of the odds ratio between my average case and my 1 standard deviation more of travel case, the odds ratio between those two is going to give me beta 1. So again, I want to be working on the predictive space. So let's talk about the expectation first. Now, let's assume that both of our best guesses are about right. Then expected value of B1 should equal ln of 0.04 divided by 0.96 divided by 0.02 divided by 0.98. This is about 2.04. So the odds of having a positive test on a COVID-19 test if you're moving around 1 standard deviation more than somebody else, based on the totally arbitrary numbers that I've invented here. I'm saying that the odds ratio is about 2.04. Your odds of testing positive are about twice as high if you're moving around 1 standard deviation more than if you're moving around 1 standard deviation less. Okay, now, because I wasn't thinking about it a whole lot when I did question 2 here, I asked what's the probability of testing positive for someone 1 standard deviation higher. I might want to be asking, depending on how well I understand odds ratios, I might want to just be asking about the odds ratios here, because then I can do that directly. And going into the second question, thinking about thinking about the variance of beta 1. Well, if I can talk about what odds ratios are and aren't reasonable, then that would give me a direct way of thinking about the variance of beta 1. If I'm thinking about probabilities, that may be a little bit harder. But for me, usually thinking about probabilities is easier than thinking about odds ratios because I don't have a big handle on odds ratios. So how might I do this? Problem here is now I've got more uncertainty I might want to take into account. So I think the easiest way, and I'm kind of doing this on the fly, but I think this should be reasonable. The easiest way I might do this would be to consider the odds ratio comparing the probability of testing positive for my one standard deviation higher group. The highest I think that could possibly get compared to the average still up here. So I'm not taking into account the uncertainty I have on beta 0. I'm just looking at my uncertainty for this new covariate outcome. So if I do this, this is going to come out to be about, let me run the numbers real quick. 0.15 times 0.98 divided by 0.02 divided by 0.85 out to about 8.65. So I think that beta 1 might be around 2.04. It might be as high as 8.65. So given that I haven't included any uncertainty about the average case here, I might want to make my quantile statement about 8.65 weaker. For example, 8.65 is equal to the expected value of beta 1 plus 1.5 times the standard deviation of beta 1 instead of 2 times the standard deviation of beta 1. Basically, I just want to account for the fact that I'm less certain about my information coming in here because it's based on an odds ratio and I don't know precisely what's going on in the most average case I can think about. So I may want to account for a little bit of extra uncertainty here. And I do that by just saying that this isn't like a 97.5% bound. This is 95% bound or a 93% bound, whatever this is going to work out to be. So this gives me a little bit more flexibility on that prior. So I've brought in some information which we could consider expert information, except I'm not an expert on this problem. But I've brought in some information to help me understand what are reasonable possible values for these parameters. And I've done that from the predictive space. I've done that by thinking about actual individuals I might sample and how the tests might come out for those individuals. And I've used that to back convert over to pieces of information I could use to build something like a normal distribution for these two betas. Now, I don't have to have particularly good information to be making priors for the betas in this way. I can be pretty expansive on what I think these probabilities could be. And that's going to be just fine because, remember, the big thing we want to avoid is we want to avoid the instability that comes in when we use an improper reference prior, when we have really extreme values of the x beta result. If we're putting this in terms of probabilities, even probabilities like 0.02, 0.10, if we're putting this in terms of real probabilities, we'll be able to translate that into betas that make sense for those real probabilities. The danger is if we don't think about it on the predictive space, we can wind up picking beta values that give us probabilities more like 0.00000001, because it's not too hard to get extreme like that. If I'm perfectly happy to say that I think this is incredibly unlikely, maybe I want to go to 0.001. That's strong, but it's not nearly as strong as a 0.0000001. And we can develop priors that can express that well. So, like I've been saying all throughout this lecture, we want to deal with thinking about our priors by going to the predictive space, by thinking about what is this going to look like on the predictive space. I think that's about all I want to say on how to apply Bayesian methods to a binomial regression model for this lecture. Like I said, next thing we'll do is we'll look at some example data and see how this all plays out. But for the moment, you've seen how to use a generalized linear model to build a binomial regression model. And now you've seen how we can write the likelihood for that model and how to build some priors for that model that make some sense, that are connected up through the prediction space and give us reasonable values. So I will sign off until our next lecture.